Hi, in this video let's take a look at this HT118A 6000 counts true RMS auto-ranging multimeter. Amazon store Kaiweets provided this meter to me and wanted my opinion on it. I had been looking for a replacement meter to the analogic EM860T that died a while ago. And while I was doing some research, the HT118A did come up quite a few times. So I'm quite eager to find out how this meter stacks up. After all, they're both 6000 counts meters, and this one surprisingly is a lot cheaper. The current list price is at around $37. If you are interested in this meter after watching this review, you can check out the link provided in the description down below. One interesting thing is that if you do a search on the HT118A, you will see multiple brands come up with the exact same model number. For instance, there's one from Hubble Test, and there is also one branded as KK Moon. I'm not actually making this one up. And it is also being sold elsewhere as just a plain old HT118A. So I'm assuming that all these different branded HT118As are essentially the same under the skin. The meter came with this rather non-descriptive box here, but the manual it came with does have the branding on it. You can see here we have Kaiweets, and also on top, on this multimeter itself, we also have Kaiweets printed on it. And you can also see that the Kaiweets are actually printed on the case itself rather than just simply taped on afterwards. So this does tell you that at least the Kaiweets branded HT118As is a volume product. This meter claims to be Cat 3 1000 volts and Cat 4 600 volts rated. I would definitely take it with a large grain of salt. But for your general electronics work and even some in-house electrical work, we're mostly talking about Cat 1 and Cat 2. So most meters on the market should be more than capable of handling these conditions without too much safety concerns. But if your life depends on it, for instance, if you are an electrician and routinely measure high energy circuitry, I would stick with a name-branded meter that has gone through the rigorous certification process instead of these no-name branded ones. And later on in our teardown, we should be able to gauge approximately what this meter is really rated for. And what came with this meter also is this pair of leads. And as you can see, we have this shrouded cover here. And this is mainly for Cat 3, Cat 4 ratings. But I don't particularly like these when doing electronics work because they really get in the way and you don't have too much of the leads here to speak of. So I usually I would just take it off for the general use, and we'll leave them off for the remainder of this video. And we also have this thermocouple, which comes in handy if you are just doing some rough temperature measurement, which this meter does support. Once you turn on the meter, you will see that there are these indicator lights in the sockets where you should be placing your leads in. And they light up ever so briefly the first time you change the range. But that's a very good indicator, especially for beginners, as to where to put the leads in. And right now, for example, we're in the current measurement range. We should be putting our leads here. And if you're doing the amp, you should be placing your leads in these sockets respectively. Now, one thing it doesn't do is that although it tells you where to put leads, but if you manage to put in the wrong sockets, for example, right now we're measuring voltage and we're putting the leads into the amp range, the amp socket, it doesn't really give you any warning. So that doesn't really prevent any damage to the meter. Now, that said, it does give you this one extra layer of protection. At least you should be checking which sockets are lighting up before you pursue your measurement. Perhaps a slight better implementation is that found in the BK Precision 2709B. in which if you, for example, it also has this warning, but if you put in the wrong leads, at least it gives you this continuous beeping. For instance, right now we're in the voltage range. If I put my leads in the amps range socket, it will give me this audible warning. That's because it has a split socket design and it detects whether or not leads are inside. And while we're on the topic, my favorite design actually for this type of protection is that found in this old Craftsman multimeter. And as you can see, we have these physical barriers, I call them shutters, that actually protect you from placing your leads in the wrong socket. As you switch in the range, you will see that the shutter covers the ones you shouldn't be placing your leads in. So that's a very clever design. And in fact, once you are in the specific range, you actually cannot really switch to a range that is not allowed. For example, right now I'm in the voltage and ohm measurement. You cannot really switch to, say, a current measurement range. You just physically cannot do that because of the shutters in place. So that, in my opinion, is the safest way to protect the inputs. But I'm not sure why, no meters, at least not to my knowledge, I have seen using this specific technique. Now let's move on to some measurements, and I think what I'm going to do is at first I'm going to use this meter only and do some measurements with its resistance, capacitance, and some other functionalities with this meter only. And later on, when we're doing the voltage measurements, I'm going to stack this meter up with a couple of other meters I have to see how this meter performs. So let's first start by taking some measurement in the ohm range, and for that I'm going to power it down, plug my leads in. And you did notice that it's a little bit of slow for the range changes, but that's actually quite typical for a lot of the cheap meters. In fact, the very expensive meters, the mode switching is not that much faster than what we see here. So that is perfectly acceptable. Now let's one thing notice is we don't really have a way to clear out the residual readings here, as I don't see any rel button that I can find. So that is something you need to keep in mind if you are measuring a lot of small resistance resistors, for example. That certainly can be a big deal. So let's take a 100 ohm and 0.1% tolerance resistor. So this is a very accurate resistor here, and I'm going to measure its value. Now let's short the leads here. And it does have that residual value, and there's no way for us to clear it out. Some meters, there's a relative button. For example, the BK2709, you can press that relative button, and that reading will be zeroed out, but we don't have that. So that might affect your small resistance measurement, just to keep in mind. So now let's do the measurement. And it's 100.2, so I suspect you also have that residual measurement there, so that might affect your reading. Now, that's not too bad. While we're still on the ohm range, let's measure a white LED, and that is something certain meters have problem with. Let's change to LED mode, and let's just, yep, here we go. And no problem, as you can see, it lights up, and also we have the current drop reading. And this is actually pretty good, considering that this meter uses two AA batteries. So the overall voltage is actually only 3 volts, and it is able to measure the voltage drop of a white LED. Not too shabby at all. Next, I'd like to measure this small capacitor, and this is a 47 picofarad capacitor, and let's see how this meter behaves. A lot of the meters would have issues measuring small capacitance just because of the stray capacitance from the leads and whatnot, and you'll get a very inaccurate reading, but let's give it a shot. So now I'm going to measure it, and it shows it's a 65 nanofarad. Clearly, it's significantly larger than the 47. Now let's just, for curiosity, see if what it really the true value of this is. For that, I'm bringing out this Agilent U1731B, this LCR meter, and let's just see for comparison. So now let's change it to capacitance measuring mode, and I'm going to calibrate it by zeroing it out. Okay, so now we are at, I'm not sure if this is a little clear, I will just tilt it a little bit. So let's put this on, and we'll see what the reading is. And you can see it's measuring at 49 picofarads. So this actual capacitor itself, the reading is pretty close to its true value. It just, these meters are not able to measure it accurately. In fact, I don't think we should fault too much on this meter. Now let's take a look at the same measurement on this BK Precision 2709B, and to see what we are getting here. We have some residual capacitance. We'll zero it out. And this is a little bit difficult here. And as you can see, also the result is it varies quite a bit. So I wouldn't fault too much on this meter's inability to read to give an accurate reading. It's just the nature of these kind of meters in general. Next, I wanted to measure a relatively large capacitor, and this one is a 15,000 microfarad capacitor. A lot of the meters, including my BK Precision and the Agilent LCR meter, cannot really measure this capacitance. And so let's see how this meter fang out here. So for that, I'm going to put it right here. And it's thinking. It takes quite a bit of time, but nevertheless, it does give a relatively, good number right in the ballpark. Of course, I have no way of knowing the true value, but 14 microfarad does sound pretty close. So I would give this a pass here, and it does look like it has the capability to measure capacitance in such large range. Another feature this meter has is this non-contact voltage detection here. So how it works is if we turn it to that mode, and if we bring in a energized socket, and it should tell us that live wire is nearby. So that works all great. But what I found out is this actually is overly sensitive, and in fact it gives a lot of false positive readings. So for testing here, I have another DC source that is just simply coming out of a power brick here, and this is low voltage. This is 7 or 8 volts. In fact, let's verify that, so that just to show you here. So here I'm going to measure the voltage. Where's my leads? My leads are here. And you can see this is it's a 7 volt DC source, I believe. 7.5 volts DC source. Okay, so that's our source here. But if you place it near the detector here, it will. In fact, now it's not doing it, but here you go. So when you put it here and it started beeping, thinking it's a live wire. So that clearly is an issue, but that is not unique to this HT118A. In fact, I found similar issue with this Onan 8009 meter as well. So for instance, if I put it to NCV here, and you will see that it's doing the same thing, but depends on where you put it. It might give a slightly different reading here. So I think that this is just some of the common features, well, the common problems rather, of all these cheap meters here. But one feature of this meter's non-contact voltage detection I really like is that it has the ability, you can switch the mode here. So for instance, right now, if I switch it to the secondary mode, what I can do here is use my meter and I can plug it into the power source and see which line is live. So I think that is actually very, very convenient. And in fact, when you are in this mode, the sensor from the top is no longer working. So that actually gives you the full control over, what you are testing with your power lead here. Now it says to use this lead only, but in my testing, I can also use a different lead as well, and I don't see any differences. So for that, I'm going to show you. If I plug my negative here, I can also use a negative lead to do the same testing. And you were saying, oh, is there any danger by accidentally touching the other lead? No, there's no danger at all, because this is a 10 mega ohm resistor in line here, so there's no danger whatsoever. So that clearly is a very nice feature I really like. Next, I want to get a relative sense of the current range accuracy of this HT118A multimeter. So for that, I'm going to use my 100 microamp current source that I built a while ago. This one has a very good current accuracy. As you can see, we will validate it with our BK Precision 2709B. So for that, I'm going to turn to the microamp range and we will see the reading here. And as you can read, a little flare here, it's a 100 and 100.1 or 100 microamp. It's right spot on. So let's turn it off. And now it's turn of this HT118A. So let me turn it to microamp range, and we have to swap the jack to this one here. Now let's read what the reading is. 99.6. Actually, it's not too bad, as it does have a plus minus few digits accuracy range in its specification, so I believe it is still within spec. So now let's move on to a 2 amp current source. For that, I'm using my lab power supply, the Agilent 66312A, to generate a 2 amp output. And let's first use the 2709B to validate the reading here. So for that, I'm going to, oops. So that's why this is important, as it's a wrong range here. And that beep just annoys you till you fix the actual jack input here. So anyway, so now we are running at 10 amps. Sorry, we're at 2 amps. So let's take a look. And you can see the reading is 2.01 amp, so that's pretty accurate. In fact, it's right around the 2 amp mark. So let's note that, and I'm going to apply the same current through this HT118A multimeter. I'm going to change it to amp mode, so now I have to swap the lead again. And now we're going to apply the current source to this multimeter. And I like how the backlight started turning red, telling you that it's a high current in this case. And it is 1.993, and a little bit of a little bit of discrepancy between this one and what we had on the 2709B, but no big issue at all. So as you can see, that the current ranges are pretty accurate as well for this HT118A multimeter. So the next set of tests is for DC accuracy test, and for that I'm hooking up all these meters to my EDC voltage standard I have out there in the lab, as you can see. And What I have back there is a Keithley 197, as that is a 5.5 digit multimeter, so it has a higher accuracy than the most of the meters I have here, so that is serving as a reference back there. Now I'm going to set the EDC voltage source to output a 100 millivolts voltage. And you can see that all the meters here largely agree with each other. Of course, for the Kaiweets, we also have a millivolt range, so we can squeeze out one extra digit of resolution here, and that also is 100 millivolts. Now for the unknown one, this one has a millivolt range as well, and because it's a 10,000 counts multimeter, it also has one extra digit. So that is clearly an advantage if you routinely measure these kind of small voltages, that you need that extra digit of resolution here. But let's switch back. Of course, for our BK precision, we also can switch this range, and you can go to the millivolt range. Then you have your extra digit of resolution there as well. So let me switch this back so that we're in the voltage range again. And now what I'm going to do is I'm going to sweep up the voltage, and we'll see how much these meters agree with each other. So now we have 200 millivolts, 300, 400, 500, 600, 700, 800, 900, and we have 1 volt. So let me change it to 1 volt. So as you can see, all the meters here are actually pretty accurate. They all are pretty much bang on whenever we change the voltage source's output. So now we have 1 volt, 2 volts, 3 volts. It does seem that the Kaiweets measured ever so slightly higher than the rest of the meters here. But again, that is well within the range of error. 4 volts, 5 volts, 6 volts, 7 volts, 8. Now you notice that we lost a digit of resolution when we switched from 6 to 7. That's because this is a 6,000 count multimeter. 9 volts and 10 volts. So besides the reading being a tiny bit of higher than the remaining of the meters here, there's no significant problem at all. So all in all, it is a fairly accurate meter, I have to say. For the next test, I have this WaveTech 395 arbitrary waveform generator out there, and it's outputting a 100 Hertz sinusoidal waveform right now at 1 volts peak to peak. So you're seeing here we have the 2 volts output reading. So what I'm going to do is I'm going to keep increasing the frequency to see at what point the measurement for this Kaiweets meter dropped out. And so that would tell you the bandwidth. And I did not see the bandwidth mentioned anywhere on the manual, so we can find out through this testing here. So now let me start increasing it. And by the way, I do like, you can see that we have a dual readout here. One is for frequency, one is for your actual voltage, and that can come in really handy here. So now we're at 300 Hertz, 400 Hertz, no problem. And so the 3 dB bandwidth would be dropping to about 1.4 volts. So let's keep a note on that, and we will see at what point we start seeing that drop. So we already see a little bit of drop, and you can see in the background here the Keithley 197 is holding out very well, because that one has a very high measurement bandwidth here. So we're at 2.6 kilohertz and already at 1.6 volts here, so it's almost towards its limit here. So and as you can see here at 3 kilohertz, this one already dropped out to its 3 dB limit here. And we have a little bit of headroom on that Anon one, but I suspect it's just a couple of 100 hertz difference here. So for instance, we're increasing to 3.3 kilohertz. Yes, that Anon one is also dropped out. So these two meters, I suspect they're very, very similar in terms of the bandwidth performance. Now, if we keep increasing this, at some point, obviously, both meters would be reading close to 0. But you can see that at least 2 meters here we have my BK Precision and also the Keithley 197. They're holding out really, really well. So clearly, if you need to measure some high frequency waveforms all the time, and this may not be the right meter for you, but for your typical measurement, especially you're just measuring the mains voltage, and this should not be a problem at all. So now let's change the waveform type to a square wave. So now let's do a square wave. And of course, now the output amplitude, I need to adjust it to be RMS 1 volt peak to peak. And again, we can see similar readings here across the board. That's important because this is a true RMS meter, so I would expect the readings largely agree. Now, interestingly, you can see that for the Anon and the Kaiweets, their readings are ever so slightly lower than the true RMS reading from the Keithley, produced from the Keithley and BK Precision. So very interesting observation. Now, again, from this very similar output on various different ranges and modes, I think these meters may be based on the same the DMM chip, but not entirely sure. So okay, so let's increase the frequency here again and see at what point we drop out. Now I would suspect it to be very similar to that of the sinusoidal measurement here. So we're at so now at about 2.7 kilohertz we dropped out. So it is a little bit narrower, the bandwidth for a square wave compared to the sinusoidal wave, but nevertheless it's only 300 hertz difference. And one last test I want to do is to measure its frequency measurement capability. Now, there's a little bit of concern after reading the manual. As you can see, I have the manual right here. It says on the frequency and duty measurement, the voltage above 10 volts cannot be measured, otherwise the instrument may be damaged. That is very interesting, as this is a Cat 3 and Cat 4 rated meter. You would expect at any range you would be able to put in the maximum allowed voltage without damaging the instrument. Now, I don't know if that is true or not, but especially it's not agreeing with the specification spec in the page here. For instance, if you are reading about the frequency measurement here, and you can clearly see the overload protection is set at 250 volts. So I'm not sure which one to trust, but for the time being, I'm going to play safe and limit the voltage under 10 volts because I don't want to right now damage this HT118A. And later on, we may do some other experiments and we will try to see if that is indeed its correct voltage limit on the frequency measurement section. But also another thing to point out is on the same page here, you see that for DC AC millivolt measurement range, do not use it to test DC above 250 volts and the instrument may be damaged. Again, that's a little bit of concern given that this is a Cat 3 and Cat 4 rated meter. So again, that's just something to keep in mind if you intend to measure the voltages beyond what is specified for the specific range. So for the frequency measurement, we will change it to frequency, and we happen to have the same capability on the Keithley, so we also want to change that. Sorry, not Keithley, on the BK Precision, so we'll change it to the frequency measurement. And also on this Onan one, we also have the frequency measurement. So now we're at 100 hertz. So again, this dual display is very useful. For the Onan one, you have to keep selecting a different, using this mode mod button to select to see the duty cycle versus its actual wave frequency. Okay, so now we're at 100 hertz, and remember this is square wave, and now I don't think the wave form matters that much. So let's just use the square wave for this measurement. Now we're going to increase to 1 kilohertz, no problem. So in fact, I'm going to increase by 1 kilohertz at a time, as I suspect the bandwidth is quite high. This is specified to be measuring several megahertz. So let's do, right now we're at 15 kilohertz, no problem. $50 kilohertz, no problem at all. Let's go to 100 kilohertz. No problem at all. So let's increase it by 100 kilohertz. 300 kilohertz. 600 kilohertz. This is 1 meg. No problem at all. So let's do 2 meg. 5 megahertz. No issues. Let's jump right to 10 megahertz. And I didn't see when this Onan one dropped out, so let's actually drop it down a little bit to see what is the maximum range for the Onan one. So it looks like Onan is able to do 9 is not good. So in fact, right around the 9.1 megahertz, 9 megahertz is where the Onan would drop out. In fact, it's lower than that. 8.9, it's already showing quite a bit of an error here. So the Onan would be around 8.8 megahertz, whereas these two meters still going strong. So that's actually very good. So now let's go to 11 megahertz. No problem. It's actually quite impressive now. 12 megahertz, no problem. 13 megahertz, no problem. 15, wow, that's still going. That's very good. Okay, so at some point, I didn't catch it, but after 15 megahertz, it seems to have some issue here. So 16 megahertz seems to be approaching the limit. Yep. So in fact, 16 megahertz seems to be both the highest for reliably to be able to measure by the BK Precision and this Kaiweets meter. Now, interestingly, I'm not sure if you see this. At 16 megahertz, that is very interesting. As you recall that at 8 megahertz that our Onan one dropped out, but right now at 16 megahertz it came back again. So not entirely sure how, why the case that is. So maybe some connection issue. So anyway, so looks like the Kaiweets is also capable of measuring In fact, now it can actually measure higher, 70 megahertz. So I'm increasing it to 18. Let's just see when this actually dropped out. 19, 20. Wow, that is really impressive, actually, the Kaiweets one. Anyway, so Kaiweets does have a little bit higher bandwidth, but again, it's not as reliable. I think I might have found out why these meters are given slightly different ranges in terms of frequency measurement, and that is because the amplitude output originally was set to 1 volt RMS. So now after I increase it to 2, I did some experiments, and you will see that these meters actually match pretty well together. So now let me just show you really quick. So now the amplitude is at 2 volts RMS, and it's still the square wave. So now let's go back to the frequency, and I'm going to just increase it. Right now you can see that at 9 megahertz there's no dropout from the Anand one, and I think I was referring to the Anand as Kaiweets in the previous tests. Apologize for that, but anyway, so let's keep increasing, and now we're 13, no problem, 14, 15. In fact, both of these are keeping up. Now you do notice while we are increasing these frequencies, you will see that the duty cycle started measuring is lower than 50%. Now that's actually an indication that something is not catching up, as you will see pretty soon that we're going to be dropping out for both of these meters. So now we're at 18 megahertz and 19, 20, so that is still going. That is actually very impressive. You can measure up to 20 megahertz. Now, of course, that is input voltage dependent. Now we're at 22. So for our BK precision, it's not able to measure this high anymore, but for these 2 meters, they are still measuring. So at the 22-ish, the Kaiweets dropped out, but the Anand one is still going. Now it's 23, 24, 25. So it looks like the Anand one, after all, might be having the highest input bandwidth and also capable of measuring the highest frequency after all. But nevertheless, these two, the Anand and Kaiweets, are very, very comparable in this regard. This video is already getting to be pretty long, and I think I'm going to save the teardown for a separate video, so we have a dedicated time for that. Now, before I finish up, I just realized I forgot a couple of things. One is the continuity test that people probably are interested in. And so when we are in this ohm range, we can change the function to be continuity test, and you will see how fast the meter reacts. So let's try it, and it is reasonably fast. In fact, not the fastest. There's ever so slight delay, but that shouldn't be a big problem. One interesting thing is you will see that if the continuity is on for maybe more than half a second, the screen lights up. So that is a interesting feature here, but it's not all that useful as it lags the sound by significant amount of time. So that's the first thing I want to show you. The second one is the bar graph. Now, this meter is, in my opinion, one of the biggest benefit of a meter like this is it has a bar graph. So sometimes you can see the variation of the voltage without the numbers being settled. And so let's take a quick look at that to see whether or not it is useful. So let's again change into the volt mode. Now I have an adjustable power supply in the background, so I'm going to hook it up, and I'm going to just randomly adjust the knob, and you can see that we do have a reasonable update speed of the bar graph. So it's not the fastest, as right now it does lag behind a little bit, but nevertheless it is useful. And so certainly that is a big benefit of a meter like this. In conclusion, the Kaiweets HT118A is a pretty decent multimeter. It has its limitations. For instance, it doesn't allow manual range override and has a pretty low AC voltage measurement bandwidth. but consider its price range. You really can't ask much more than that. In the next video, we will do a teardown and to see what compromise it has to make in order to achieve such a low price tag. I hope you enjoyed the video. If you liked the video, please remember to give it a big thumb up and remember to subscribe, share. I will catch up with you next time.